All right. Okay. Well, good morning. Happy Wednesday. Um, and I guess this is our kind of last call to sign up or get your groups together. So the deadline is tonight, I guess around midnight. And then so probably sometime tomorrow, I will take everybody who is not in a group, okay, and just kind of arbitrarily assign them to groups. So, at the very least, you should put in some of the information, and I'll do my best to try to match up people according to what they've put on the Google Sheet. But some people still haven't put any information in there, haven't put in a group. I'm not even sure if you're watching these videos, but you will get assigned to a group. So my hope is you'll contribute to your group project. Everybody else, thank you for signing up and filling out your group information. I'll kind of go through, and again, the deadline is tonight at midnight, and I will, or 11:59 p.m. To have your group information in there, and then probably sometime tomorrow I'll just arbitrarily assign everybody else. Okay, let's see. So we are, let me publish this view quiz. Okay, so we have been talking about just kind of exploring our data, okay, taking a look at it. And so those of you who are in groups, your assignment right now is to kind of look around and try to find an interesting data set. Try to find a data set that you are interested in analyzing, that would be able, where you'd be able to kind of, do some subgroup analysis, do just something, okay, where we hope you can find something meaningful or interesting in the data. And again, in the kind of final project, I have this sheet with information on finding data, and then once you get your data, you should always we talked about importing it on Monday. In Monday's lecture, we talked about importing your data. And so, once you find something that you are interested in, import it and take a look at it and ask questions about, does this data look valid? Is it internally consistent? Does it look like it's a trustworthy data set that we can use? These are during the 6th week. I will meet with all of the groups as kind of you're in a proposal meeting where I will take a look at the data sets you've selected, and I'll only have maybe 20 minutes or so to kind of look at it, but I feel like I have enough experience where if there are any glaring issues, I notice them fairly quickly. So I'll be asking all of these questions about the data reliability and whatnot, and then you will tell me what kind of, in your project proposal, you'll tell me what kind of questions you have that the data might be able to answer. Okay, and then just as you find data sets, just do like the most basic data analysis where you'll start exploring maybe one variable at a time, maybe two variables at a time, and we'll as we work through this, I'll give you more and more examples of all of this. So that is your assignment now. You have a DataCamp homework covering ggplot that's due this weekend, and then you have your second homework assignment due on Friday. I hope that's going okay. And yeah, okay. So let's see. Today, what I want to talk about is this concept of pivoting your data, okay? And basically turning your data set into a form that is useful for the functions or the analysis you want to perform, okay? And so we are pivoting, or another way to think of this is reshaping, okay? Reshaping our tables. So we are not like changing or altering our values, but we are reshaping the structure of our table. So, when you find a table on the internet, you'll have rows and columns. That's kind of the most common form. But sometimes the way those rows and columns are formed or arranged may not be the most useful for what it is you're trying to do. And so sometimes it requires you to reshape it. Other times you don't have to. Sometimes, depending on the kind of analysis you want, you might want it in one form, and you might need to reshape it into another form, and you'll use both forms of the table. I'll give you some examples of this, okay? Just because right now I'm kind of speaking in this hypotheticals. This is related to chapter 6 in our textbook. They have a lot of examples here, and kind of the basic principle that we want to kind of follow and use is that every row contains just one observation, okay? Or whatever your observational unit is. And so it could be, and it, again, how you're doing your analysis could differ from one type of thing to another. So you might have every observation is a person, okay? And that kind of makes sense, right? But then, and you would when you do your analysis and you say like, okay, what is the average age? Okay, it would be, what is the average age of kind of each person? You have 100 people or something, and you take, add them up and you divide by 100. Okay, that's your average. But you could also rearrange your data so that perhaps each row is a group, okay? And so your original data set might have 100 rows, but you might rearrange them so that each row is now a group, and you'll kind of rearrange them so that the people, each row will have, this will be like group 1, and you have these 4 people, and this is group 2, and you have these 4 people, and you have group 3, and you have these 4 people. And then, and so you might have like 25 groups. And so you might have to kind of restructure that. And then in that case, the questions would be something like, you wouldn't want to ask what is the average age, because that applies to individuals, but you would ask something that was relevant to the groups. For example, what is the average size of the group? Or what is the average, within a group, what's the, I don't even know, like average percent of, proportion that, is in this major or something like that, okay? And so that might be the case there, okay? But anyway, so each row contains just one observation or one observational unit, and each observation gets its own row. Every column is one variable that we're interested in, and so and the flip side is each variable appears only in one column. You don't want to have one variable kind of split across multiple columns. And then every cell is a single value. Now, there is an exception to this. You can have cells that contain multiple values in it. That is but as far as kind of like numbers, generally we generally want to keep it down to like one number. Okay, so here's an example where you might download an Excel file from somewhere on the internet, and the data will be presented kind of like this, okay? And within the worksheet, you'll have these kind of subtotal lines and things like that, which certainly if you're printing something out in Excel, these are handy things to have. But as far as if we were to import this directly into R or something, we won't be able to start doing analysis right away, because this line with the Ward 1 subtotal and the Ward 2 subtotal, this would throw off our analysis, right? So if I just said, hey, I want to kind of like go through the precincts and get like the average number of registrations, looking at this, our average number of registrations are somewhere in the double digits, 50, 30, 40, something around there. Okay, but then you also have these lines that have like 509 and 373 because they are subtotals. And so if you just kind of took this column, and then you also have this total up here, right? And if you just took that column and you said, hey, calculate the average of this column, these numbers are going to throw everything off. Okay, so if you were to import this into R, you have to basically delete these rows or clean up your data in some kind of form. Okay, so so this is a relatively easy fix. Basically, anything that's like this, you just kind of delete that row, and then now you're just left with each row is a certain precinct, and that makes it easier. Okay. When we think about variables, broadly speaking, there are two main types of variables. We have categorical variables and quantitative variables. We talked about this briefly. Categorical variables tell us a type or category. Often they take the form of a word, so it'll be kind of like, what color is someone's hair? And we have people with black hair and people with brown hair and people with blonde hair, and we'll say, this is the word that describes that category. Okay, but other things that kind of look like numbers can be categorical. So an example I used was area code. Okay, area codes look like numbers, but they don't actually have a numeric quantity. It doesn't make sense to do a numeric comparison to say this person whose area code is 818 has more area code than this person whose area code is 562 or something like that. Doing that kind of numeric comparison does not make sense. Okay, you can, if you are able to do numeric comparisons, then it's going to be a numeric variable. And so I don't have it listed here, but the other example I gave was the date. Dates are numeric, even though they're formatted in the weirdest way possible, right? Today's date is April 23rd, 2025, but it's a kind of, you think of, you have like numbers on a number line, and basically like 5 is this location and 25 is this location. The distance between them is 20, okay? And if you think about dates, you could think of, well, at least on Earth, we have a linear kind of timeline, just ignoring the effects of gravity around black holes and stuff like that. But just, you think of dates on Earth being on some timeline, and we have this moment in time and we have this moment in time, and we can say there is 20 days between these two moments in time, or there's 20 years or whatever it is. It's just, how do we put this location in time? We don't just say like this is day 5 and this is day 25. It's April 23rd and this is April 28th, or May 15th, and then you have to do some weird like how many days were in April, and then try to figure out the times between them. But you can kind of think of them as, again, like locations along a number line or a timeline. And so dates are numeric, as funny as it seems, okay? At least moments in time are numeric, okay? And dates I would consider as moments in time. But then like the month of January, and we're talking about like all Januaries in history and stuff, like that would be categorical, and it's just kind of like weird, right? Okay. We have other kinds of variables that are kind of in between. Ordinal variables are something that's in between categorical and quantitative. Ordinal variables are categories that have a natural order, but not necessarily an objective numeric value. So if we're talking about like clothing sizes, you have small, medium, large, extra large, okay? And so there is a natural order. We would expect extra large to be bigger than large, bigger than medium, bigger than small. And you can say it's something like, I'm 2 sizes larger than, than I was 10 years ago or something like that, right? But it's not like this universal agreed upon thing where small converts into a certain number, or medium, right? And that's why like buying clothes in different countries is always kind of like a tricky thing, because we don't have agreed upon things. Whereas 10 kilograms in the US is the same as 10 kilograms somewhere else, okay? And then we also have text variables. Text variables look kind of like categorical variables, but categorical variables, generally we restrict categories. Like we'll say, I don't know, you have to, with categorical variables, you can think of like having a drop-down list, like when you're filling out a form and there's a drop-down list and you have to select one of the options in the drop-down, okay? Whereas, so it'll be something like, which state are you from? All right, and there's 50 states that you can pick, okay? And so that would be a drop-down, okay, with 50 options to choose from. Whereas text variables, those are not restricted, and you just type in whatever you want to type, right? And analyzing text is a very big part of data analysis these days, but it's certainly a lot more complicated, and I'm going to just say it's beyond the scope of this introductory class, okay? But there is a lot of kind of interesting stuff. Okay, regarding categorical variables, sometimes the categories get kind of converted into things that look like numbers, okay? So I don't know, like if you go to the makeup section at a store, or the hair coloring section at a store, okay, the color you might want to select might have a numeric code. And this helps you kind of just like pick out the same color later. You're like, oh, I really like this particular color and shade, and instead of having to remember some weird name, you just say, oh, the code was 565 or something like that, okay? But that is not a number. I mean, it's not numeric. Again, we can't take two things, and there might be like some kind of arbitrary order, but you can't necessarily take, this product which has code 240 and this product which has code 260 and say this is, a 20-point difference between, these two things. And as they number these products, there might be some semblance of an ordering, but generally it doesn't make sense to try to use those color codes and do math with them, okay? So they are not numbers, okay? So, I said hair color brown could be 1, and hair color black could be 2, and hair color blonde could be 3. And again, once you have these things, they look like numbers, but it doesn't make sense to do math with them. It doesn't make sense to add them or subtract them or things like that. And the same kind of thing with like, I don't know, like makeup colors, right? Like I think, like in the makeup aisle, you might have like this lipstick which has this certain number and something. It doesn't make sense to do kind of like math with those numbers there, okay? And so it's a very, very big mistake to treat these numeric codes as if they are numeric values. And this is something that I will, if you do this in your final project, I will like be very upset with you and deduct lots of points, is to try to do math or arithmetic with things that are not actually numbers, okay? So if you say, all right, we're going to take person with hair category 1 and person with hair category 3, and we're going to take the average of those things, that is wrong, okay? And then on the flip side, we can take numeric values and then make them categorical. So you could take something like age, and then we can split it and say everybody who's under 18 is a minor, everybody who's 18 and older is a senior, okay? Or we could say everybody who's between this age and this age, or born between this and this, is considered, Gen Z, and this everybody between this age and this age is, millennial, and Gen X, and what else is there? Gen Alpha is next. What age is Gen Alpha? Is that 2012? And okay, so how old is Gen Alpha right now? 13? Okay, everybody Right. And everybody here is comfortable calling themselves Gen Z, or do you feel like, oh, that's not me? I'm part of a different generation. I'm definitely millennial, I think. I don't know. I think so. Okay. Well, anyway. Okay. So anyway, our observational units, what exactly counts as an observational unit could vary. And so anyway, here is this same kind of data from the Minneapolis thing after we've removed these subtotals and things. And this makes it tidy in that each row is now a different kind of precinct within the city. Okay, so I guess the city is divided into wards, and those wards are divided into precincts. And so we use the ward and precinct combination to kind of identify a particular row. Okay. And then here, each row is each individual ballot cast within the election. So I guess they looked at this and I guess they do ranked choice voting, which is kind of cool, where you say, like, this is my first pick, this is my second pick, and this is my third pick, and then if your first pick doesn't win, then it takes your second pick and then casts a ballot for them, and so on and so forth, kind of like that. Okay. All right, so here, look at this. We have Jane Polanic, 1974, female, 32. Okay, Jane Poole, 1948, female, 55. Jane Poole, 1948, female, 56. Jane Poole, 1948, female, 57. Okay, in this case, what is the observational unit? Each row, what does each row represent? Yeah.
Like the birth year and the record of the runner's performance, like when they separated?
So it's not, well, it is, each row is identified by their birth year, okay? But we have, if we just say Jane Poole 1948, we have 5 entries for Jane Poole 1948. So how is this first row and this second row and this third row for Jane Poole 1948, how do they differ? The year, okay? So this is a table where each row represents basically someone's performance in a particular year. So we're allowing the same person to participate multiple times at different years, okay? So we had Jane Poole participate in 2003, and Jane Poole participated again in 2004, and then in 2005 and 2006. And so each row here, okay, is going to be a person in a particular year, their performance in that particular year. So that's going to be our observational unit, okay? And so in that case, the age changes from year to year, so that's why that's a variable. And we might want to do an analysis where we say, okay, does performance change with age and things like that? And I guess gun is how they measure the speed race time, because I don't know, I guess a 10-mile race, I think the way they do it now is they have, like, everybody has little trackers, and when you like in a big marathon or something like that, there will be like a huge number of people at the start, and so when they start the gun or start the clock, they don't actually start your stopwatch until like your tracker crosses the starting line, and that's when your stopwatch starts going. And then when you cross the finish line, they'll cut that, and then they take the difference between your start and end time there. Okay. So you'll have two people cross the finish line at the same time, but their like calculated race times are different because they had different starting times. Okay, so anyway, all of that to just get down to like what is an observational unit and then reshaping our data. Okay, wait, have I given you any UQuiz answers yet? No, none. Okay, first one today is the letter D. D as in dog. I guess I'll give you your second one also. And second one is C, C as in cat. So we have D as in dog and C as in cat. All right, so this we would say is in tidy form where each row is an observational unit. And so here these are like different storms or I guess hurricanes, tropical storms. We name our tropical storms. Like each year, the first storm gets a name with an A, and then the second storm gets a name with a B, and so on and so forth. And then we measure the wind speed and the pressure and different kinds of things like that. And so each row is an observational unit. The different variables we're keeping track of or have recorded is storm, the wind speed, the air pressure, the date of the storm, or I guess the date when it was first recorded, and and some advantages are in R, and when we do analysis, calculations can be done kind of row-wise. We can say like, hey, what is the pressure divided by the wind speed? And it will do it. It will calculate that number for every row. To do 1,007 divided by 110, and then it'll do 1,009 divided by 45, and 1,005 divided by 65, and so on and so forth. Okay. Over here, the way this is arranged is we have different countries. Okay, France, DE is Germany, and US is the United States. And then we have the columns are different years, and then we have how many cases there were of some fictional disease. Okay, and so in France in 2011, there were 7,000 cases. In 2012, there were 6,900 cases. And in 2013, there were 7,000 cases. And, you know, this is fine if we wanted to say like, okay, how many more or fewer cases were there in 2012 versus 2011? We could do calculations like that. We could say take the number of cases in 2012 and subtract off the number of cases in 2011. And we'd say France went down 100 years and stuff. But we also might have a different kind of way to do the analysis, and perhaps we just want to get like plot some of these things. Okay, perhaps we want to plot the number of cases. Okay, and in that case, I want to put like the year along the x-axis and the number of cases on the y-axis. Okay, and if I want to put the year on the x-axis, now I'm in a little bit of a pickle, because remember with like ggplot, your variables have to be in a column. Okay, and I don't have a column for year. I have a column for 2011, a column for 2012, and a column for 2013. But what I want is I want a column for year, and I want like 2011 had 7,000 cases, and 2012 had 6,900, and 2013 had 7,000 cases. And we could have, and we'll have country, and we can kind of like color our dots by country or something like that. But if I wanted to put year on the x-axis and the number of cases on the y-axis, this data would not work. Okay, so I would have to reshape the data. Okay, so in that case, if I wanted to have a column for year and a column for the count of the number of cases, my data is all kind of spread out over here, and we don't have one column for each kind of thing. Okay, here is another table, and here I've got New York, large particles 23, New York small particles 14, London large particles 22, London small particles 16, Beijing large particles 121, Beijing small particles 56. Okay, that's fine. Okay, and I could plot this, and I could say along the x-axis let's put the city, along the y-axis let's put the amount, And then let's color the bars by, we can do position dodge, and we can have like large and small or something like that. And that would be fine, okay? But what if I wanted to do an analysis where I wanted to say, okay, what is the difference between the number of large particles and the amount of small particles? And I wanted to do like, okay, New York has 9 more units of large than small, okay? And London has 6 more units of large than small. And Beijing has, 65 more units, large versus small. And if I wanted to do that kind of mathematical analysis where I'm comparing these things, I can't do that. I can't just take the large column minus the small column, because I don't have a column for large and a column for small. So this would require reshaping our data as well. Okay, so here if I wanted to, I might want to have a column where we have the amount of large particles or the amount of small particles. And our data is kind of arranged in this, inconvenient format here. So working with these things would require us to what we call reshape or pivot our data. Okay, the data sets are available online, and you can just do read_CSV, put in the URL, and it brings it in. Okay, so again, when you have the data in the columns, separate columns, and each row is its own observation, you can do calculations like, say, the ratio, where I want to do take the pressure and divide by the wind, and it will, what we call, vectorize the operation. Okay, it will, for each row, it will take this number 1007 and divide it by 110, and it will give me 9.15. And there's a few ways I could do this. I could do $ notation, and I could say take the pressure column, storms $pressure, divide by the wind column, storms $wind. Okay, in the tidyverse, I could have said mutate, which will create a new column, and we could say that new column ratio is equal to pressure divided by wind. But basically, the operation here is it's going to take each value, 1009 divided by 45 gives me 22.4. 1005 divided by 65 gives me 15.5. And it's going to do this operation for each row. And that's convenient, okay? So a lot of times you'll want to do something kind of like this, okay? But here's our table of cases. And again, this is fine if we wanted to say, like, okay, how did 2012 change from 2011? And we want to do like the column of 2012 minus the column of 2011. That would be fine. But if I wanted to do some kind of plot where I want to put like the year on the x-axis and the number of cases on the y-axis, okay, we need to reshape our data. And so if we did that, if I wanted to reshape my data so that I'm going to have a column for the country, a column for the year, and a column for the number of cases, how many rows will I end up having? If I have this table, I'm going to have one column for the year and one column for the number of cases, and I guess a column for the country. How many rows will I end up having? I'll end up having 9 rows, okay? Basically, each value here will get its own row, okay? So we'll have France in 2011 had 7,000, France in 2012 had 6,900, and France in 2013 had 7,000. And then Germany in 2011 had 5,800. And so the table would get rearranged kind of like this. Does that make sense there? Okay, and so this operation where we went from having 3 separate columns, our values spread out in 3 separate columns, and we put them into one, this is called pivot longer. This operation takes our data and we are pivoting our data, okay? And in this case, the resulting table will have more rows. And so we say we have pivoted it longer, okay? And basically, we are taking the values in these 3 columns, the columns 2011, 2012, and 2013, take the values in 2011 through 2013 and pivot those values basically into one long column of values, okay? And then the names of those columns, okay, 2011, 2012, and 2013, we're going to put into a new column, and that new column is going to be called year. So the names, the column names, will get put into a column called year, and then the values will get put into a column, and we're going to call that cases. Okay. Now, if you don't specify this names to and values to, it will just get the default name of names and value. Okay, but here we want kind of called names to be called year, and case the values to be called cases. Now, these are arbitrary names. Okay, year and cases make sense, but technically you could use any kind of thing. Okay, so here, if I want to call it when it happened or how many, we could do this. Okay. Let's say you pivot only columns 2012 and 2013. Okay, what would happen if you pivot only columns 2012 and 2013? Okay, basically it's going to take the value in these two columns, combine them, so we'll get one new column, and that new column will have 6 rows in it. Basically, the 3 rows from 2012 and the 3 rows from 2013. Okay, and everything that doesn't get pivoted just gets duplicated. So this is going to be weird, but basically that column 2011 just gets duplicated. So, it makes sense kind of France gets duplicated across in Germany and US, but also any column that you didn't pivot just kind of gets repeated and duplicated down the line here. So this is what you'd end up getting. Okay, so, just be careful that when you pivot, I guess you pivot the correct columns and you do it right. Here, if I try to pivot the country, all right, so this is something you wouldn't want to do, but if you pivot too many columns, it's going to do the same. It's going to pivot them. It's going to just combine all of the values, all of these values down here. It combines them all into one column. Okay. In the beginning, it would throw an error because it says, wait a second, you're trying to combine characters and numbers together, and I don't like to do that. But you can kind of twist its hand or twist its arm and say, yeah, just force all of the things together, and it will. Basically, all of these values, France 7,000, 6,900, 7,000, all got combined into this one column, okay, called value. And then the column names all end up over here. So the column names were country 2011, 2012, 2013, and they all got pivoted as well. Okay, so this is not going to be useful. This would be kind of not a very helpful table for us to have. But yeah, so let me. Where did the data sets go? Let me just copy these lines. And I want to. I should keep going because I want to do some more demonstrations here, but I don't want to run out of time either. Okay, so again, depending on what you're trying to do, having your data in one form or another and pivoting them will serve your purposes. Okay, having your data in this form could be acceptable depending on what you're trying to do. But if you wanted to do a calculation where you're calculating the difference between the number of small particles and number of large particles, we would need to pivot our data as well. So sorry, let me just. Okay, I'll do that later. So if I want to pivot this data, okay, and I want to have a column for large and a column for small, how many rows will I end up having? I'll end up having 3 rows. I'll have a row for each city, okay? I'll have a row for New York, and then a column for how many large particles it had, and a column for how many small particles. And then I'll have a column for London, a row for London, and then I'll have another row for Beijing, okay? So this is how our data would get rearranged if we pivot this, okay? And so this is what we call pivoting wider, okay? So you can end up longer and you can end up wider. In this case, because we basically went from 2 columns to 2 columns over here. So city remains city, but then size and amount became large and small. it's not any wider, but sometimes you have like multiple entries and then it truly does become wider and you have more columns. Okay, but basically we went from these 6 values in one column, got arranged into 6 values across 2 columns. Okay, so none of the values are being altered or changed, but they are being rearranged or pivoted. Okay, we're reshaping our data. And so this operation is called pivot wider. Okay, we're gonna pivot the pollution table. The names, large and small, come from this column size. So it says names come from where? Size. The values, okay, these 23, 14, 22, 16, they came from the column called amount. So the values came from amount. And that's how this gets arranged. These are basically the different things there, okay? Now, pivot wider is very sensitive to kind of spelling differences and things like that. So if I pivot this wider, so here I have New York and NYC, and then London and Beijing. And basically, if I try to pivot this wider, I will get a separate entry for New York and a separate entry for NYC. Okay, and in this case, it says, well, I don't have an entry for NYC small, so it puts in an NA, right? So we have NYC large is 23, but I don't have anything for NYC small. Okay, and then we have New York small is 14, but we don't have anything for New York large, so that gets filled in with an NA. Okay, and sometimes that's fine. You have NAs. You can also put in fill values of 0. You have to be careful because things are different, right? Like I could say, what's the average number of large particles? And we would do 23, 22, 121. If you have a misspelling and you end up getting 2 entries for New York like this, NYC and New York, and you have an NA, that could throw things off. You can fill those values in with a 0, but now if I said, hey, what's the average of large particles, like the 0 gets averaged in there and it throws things off. So, all of these things are these are errors that you might end up inducing by, I guess, just not paying careful attention to some of the details there. Okay, again, spelling differences can make a difference here. So here I have large spelled with all caps. We have small and large and things like this. And if I say, hey, pivot this wider, okay, what it's going to do is it's going to look at the size column and it looks for unique values of size, and each unique value gets its own column. So we end up getting a column for all caps large, a column for small, and a column for lowercase large, right? And this is probably not what we wanted, but this is just what happens because we had spelling differences. So these are just things that you got to kind of be mindful of and wary of. And so anytime you take a data set, just, again, do some kind of cleaning check to make sure the values will work well, okay? And if you do a pivot wider operation and you end up like with way more columns than you expected or something, more rows than you expected, go through and try to see where things went wrong, okay? But pivot longer and pivot wider are inverse operations. So here's that pollution table and I can pivot it wider into this form. So I had 6 rows here. These 6 values got pivoted into these 3 rows, okay? 3 rows and 2 columns, the same 6 values. But I could take this table, which I've currently called W, right? And I could pivot it longer and back into the original form, okay? Same thing with the cases table. I could do this and pivot them longer, or I could take that table and pivot it wider, okay? And again, it all depends on like what kind of operation or what kind of graph you are trying to make. So again, with the cases table, all right. Okay, so let's bring in the cases table, and we'll bring in the pollution table. And let's say I wanted to do, like ggplot of the cases table, and so right now my cases, I got 2011, 2012, 2013, right? So I don't have a good way to kind of plot this. So what I have to do is, if I try to plot this, I guess ggplot of the cases table, and I do AES, and I could think, okay, well, X is going to equal 2011, and then Y is going to equal the cases, and maybe color is going to be country. Oops. And then we want to do geom bar. Okay. Stack count must have only in. Did I do something wrong? X or Y is the right. Oh, not bar, geom column, sorry, that's why. Making mistakes here, okay. What is, Y? So actually, yeah, actually I don't know. Y would be the number of cases, I guess X would have to be country, right? Column would be country, and then why is this all bad? I guess it'd be film. Okay, so I can. This is for the year 2011, Germany, France, U.S. But if I wanted to say like, okay, how has it changed across time? This is not going to work. So what we have to do is we have to pivot it longer. Pivot longer, and what I want to do is I want to pivot the columns 2011 through 2013. Okay, and then the names to is going to be year, and then values to will be cases. Okay, so this is in a form that I like. Okay, so that's I can pivot that longer, and then now that I've pivoted this longer, now I can do ggplot, and I can do X is going to be year, and then Y will be the cases, and then the fill color will be our country, and then I can do geom underscore column. I keep forgetting we don't put our things in quotes here. Okay. Oh, and then we'll want to do position equals dodge. Okay, so this is what we have: 2011, 2012, and 2013. Perhaps. So this is how our cases have changed. I could do year is X is country, and fill is year. That would also work. Okay, and then we have this is how it changed in Germany, France, and U.S. and things like that. And we can see this is probably better. Okay, color. We can do year, and instead of geom column, I can do geom point, or maybe geom line. Is that not right? No. Let's do Y is the year, color is country. What am I thinking? What am I doing wrong? Each group consists of only one observation. Okay, point color equals country. All right, and then so we can kind of plot it that way, and then connect them with lines and whatnot. Okay, all right. Anyway, we'll end here. And your last view close answer is A as in apple. And again, just think about the form, what function you want to do, and if pivoting will be helpful to achieve the function that you need. Okay, we'll wrap up there, and we'll see you on Friday.